Welcome back YouTube to the ASX Portfolio channel. My name's Jonathan. So today we're going to be talking about beta weighting your portfolio. How do you do this with stocks and options? How do you get a risk adjusted term for what you can potentially gain or lose? So let's just jump straight into it. Let's start by importing the dependencies. So for this we're going to need to import date time as DT. We're going to need to import pandas as PD. We're going to need to import numpy as NP. We're going to go from scipy. We're going to import the stats module and from pandas data reader. If you don't have this last one, feel free to pip install it now, or conda install, whatever you're doing. Import those dependencies. Excellent. So next we're going to specify the date range for analysis. So we need to import some kind of data between dates. So we're going to use the date time module to grab a specific start date. So let's say from the start of this year, and an end date we're going to use as today. So we can just go date time dot now, and we'll check those start and end dates. Awesome. So let's select the stock information that we want over that time horizon. So let's come up with a stock list. So in my portfolio today, always have the major banks. So we'll have CBA here in Australia, NAB, Westpac, ANZ, and we'll throw in another one there, WPL, so an oil stock. Now you'll know from the Yahoo Finance data that we actually need to add .ax. So stocks equal to, so what we're going to do, we're going to add the string .ax to all the Australian stocks within this list. Now if you type something like Apple in this string here, you don't need to do this. So my advice is go to Yahoo Finance and work out what the actual code is you need to hit. Done a video on that before. So the other important information we need to do for beta weighting is add in the market index or the thing that you want to reference in terms of your beta weights. So for reference here, we're going to be using the ASX 200 index, and that's this following symbol here in terms of Yahoo Finance data. So let's just give back the stocks there as a list. There's our 5 stocks there on the right hand side, and this is the market index that we're going to be referencing to. So now we can actually go ahead and get the pandas data reader information. So let's do that. So we're going to create a data frame. We're going to have pdr.getData Yahoo, and we're going to hit all those stocks between start and end date. Once we've got that information, we want to calculate the log returns. So we can use numpy for this. So np log will take df of the close information. We'll take the shift operator of the closes with 1. So shift 1 close information. And the reason we're skipping over this a little bit is that we've done this numerous times over the last couple of episodes. So if you don't know what I'm doing here, please feel free to go back and watch those episodes. So here we're just calculating the log returns for that data. Awesome. So now we're going to go through 3 different methods for beta weighting, for actually calculating beta. So the first one we're going to do is directly calculating beta using the covariance between the market and the stock divided by the variance. So let's just get cracking and create that function. So we want to define this function. We're going to call it calc beta, very original. We're going to take in this data frame, df. What we want to do is return a pandas data series with all the betas with the column names. So df columns is how I refer to that columns within the data frame. And I just want to take from the market index onwards, so only the stock information. We're going to name this data frame beta. So always important to know what you actually want to be returning. All I want is the betas against the market index for all of the stocks. Cool. So now that we got that, let's get cracking. We're going to make a numpy array. So we're going to define that by going .values, df.values. So it's important to know that the market index in my data frame is the first index, first column. So yours might not be. So this is really important. Wherever you've put it in this list is extremely important. I advise you to do whatever index you're looking at in the first column. So np array, and we're just going to reference all the rows but the first column. We're also going to make an empty list for beta. Now what we're going to do is we're going to iterate through each one of these columns. So for index and column in enumerate data frame. So the enumerate gives us back the index and the value is the column for this data frame here. So if the index is greater than 0, and what's that saying is don't give us the first column because that's our market index. So if index is greater than 0, then we want the stock returns indexed by this ind. So let's go stock returns s equals numpy array, and similar to how we got the market index here, we'll just index by ind to get the correct stock information. Now what we have to do is calculate the covariance matrix between the stock and market. So what we're going to do for that is just define the covariance as using numpy, so numpy.cov, and we're going to take the stock, we're going to take the market, and it's as simple as that. So now that we have that information, we can use the covariance matrix. We know that on the diagonal, we can actually get the variance, and we know that the formula for this is just covariance of the market and the stock divided by the variance of the market. So let's append the betas that we're about to calculate to that list, and we're going to take the covariance, and we're going to take the, now remember this is covariance matrix, so we're going to take the part of the covariance between S and M, and we're going to divide through by the variance, which I guess is the covariance of the market against the market with itself. So this is our covariance of the market and the stock divided by the variance of the market. And that is equal to our betas. So now that's great. If we hit enter on that, and let's run this against our log returns. What have we done here? Have we spelled enumerate wrong? Yes, we have. Enumerate. Excellent. So now that we've calculated the betas, let's go ahead and try and do this another way. So another really useful way is that you can understand that this is just linear regression. So we're essentially putting a straight line through the returns of the market and the stocks on either axis, and then doing linear regression, OLS, line of best fit, to try and find the coefficient, the relationship between these two things. So what we can do is actually use the scipy stats module in a very similar way to what we've just done here. So we're going to copy all that, but we're going to call this function now regression. So regression beta. So in the same way, we're going to take this numpy array data values, we're going to take the market index, we're going to leave something for beta, but this time we're not going to do any of this. Actually, I stand corrected. We are going to keep the stock returns indexes, but the final point here is we're going to use linear regression instead of this covariance divided by variance formula. So what we can do is go beta append. So what is this beta append going to be? Here we're going to use the stats module, lin regress. So scipy, stats, lin regress, and we're going to take market and s with each other. So important to know that this function right here does give you a whole bunch of things back. But if you index on the first variable that comes back from this function, you're going to get the actual, the gradient, the relationship between both of these variables. And that's what we want. That's what beta is. So we're indexing by 0 there. So we're still getting our betas in here. We're still taking the columns. Excellent. So now that we've got this function, let's make sure that we get the exact same betas that we've just worked out there. So you can see completely different function, different methodology, but we have the same betas. So this is just another tool in your kit that you can use to calculate these things. Now, both of these methods aren't very clean. We're iterating with every column of every stock. It's kind of building up a list and then building a data frame. It's kind of tedious. Now we can use, because this is linear regression, we actually have a closed form solution for this method. So thanks to matrix algebra, you can go to this Stack Exchange link here if you really want to find out more. But essentially for linear regression models of this form, it's a closed form solution. And essentially with this argument and minimization function here, you get the estimates of the betas that minimize the differences between the errors terms as this. So what we're going to do, we're going to implement this in matrix form using NumPy arrays, and it's going to be a whole lot cleaner and a lot less lines for us. So let's start this function from scratch. So we're going to call this matrix beta. So also just a comment with that, we are going to be returning the exact same thing. So all these betas are going to be equivalent. So if you don't want to learn how to do this, just skip forward to the next section. So we're going to have the betas df columns 1 onwards, and we're going to name this beta as well. So all of these are returning the exact same thing. So here, again, we have the market index. And don't forget, that's at the first position. So we're going to call this x this time. So df values, index the first one, take the first column. So now that we have x, what we need to do is we're going to treat this like it's the final solution. So we actually need to add an intercept column into this matrix. So add an additional column for intercept, and we're going to initialize these values as 1s. So the way you do that in Python, we're going to go np concatenate, and we will just have, we're going to take in this x as the second column, but for the first column it's going to be np ones like, which just says give me a structure of ones that's in the same form and size of x. So we're going to have a bunch of ones on the left hand side and then our x values on the right hand side. So pretty easy. We have to make sure that this is axis equal to 1. If you don't know what I'm doing there, just feel free to look up numpy concatenate. So now the hardest part of all this, and we're going to do it in one line, is we're going to apply the matrix algebra. Geez, if I can spell algebra, for linear regression. closed form solution. Easy. So we're going to directly calculate the beta, and this is just going to be numpy. So we're just copying this formula right here. So we need to use numpy linear regression, linear algebra module, sorry, linalg.pinv. So this is going to give us the inverse to here. So first off, we need to do the transpose of x. Now, someone on the channel commented that I can use not dot, but I can use this at for matrix algebra. So thank you very much for whoever that was. So I can just use this at operator to do matrix algebra. So we're taking the transpose of x times by x, taking the inverse of that. We're then multiplying that by the transpose of x dot t, and then we're going to matrix algebra multiply that by y. Now y here, remember, is the df values of all the stocks. So what we're going to do is take all the rows, but we only want the columns from after the market onwards. So important to know here that we're going to get a whole bunch of betas in this. We also get another variable of the intercept. So we're going to get the intercept indexed at the 0 position, and we're going to get the actual value we're looking for, the coefficient, as the first or second placement. So we're going to index by 1 to get that there. So after we apply that, hopefully I can convince you that this has all worked. And there you go. You can see that all of these coefficients are exactly the same, which is really cool. So look, you've just learnt 3 different ways of calculating beta. Why the hell do you want beta? Well, that's a really good question. Let's do this second part to find out. So I'm going to make this last one equal to beta so we can use it for the next couple of sections. So let's calculate and define our portfolio. So I'm going to build data frames. It's going to take a while. It's going to be a little bit tedious, but please hold out. It'll be worth it. So we're going to define the number of units of each of these shares. So we're going to take a numpy array. I'm just assigning pretty much random portfolio units here, but yeah, again, you could use your portfolio that you actually own and place the units that you own here. We're going to take the ASX prices. Now remember that was df close, and if we index by -1, we're going to take the last row of that index to get the final closing prices. We'll convert that to values and then to a list, and we'll be taking the 0th index of that. So again, just getting a list of the ASX prices. Now for our price column, we're going to have a numpy array, and I want to round these prices. I just want to make it clear, maybe to 2 decimal places, what we're trying to do here. So we're going to round price for price in ASX prices 1 onwards. Now I don't want to list the index. That's not part of my portfolio here. So remember, I've got 5 stocks. So I'm just trying to get the 5 prices past the index. So next we're going to take the value. So we're going to just get the value of this portfolio and individual weightings by multiplying the units by the price. Cool. Next part is we're going to get the weight. So the weights are predefined, I guess. So we've got round value divided by the sum of value rounded by 2 for val in value. So I'm just taking this whole list of value for the units times the price of each individual stock, and I'm getting the percentage value compared to the whole portfolio. Hopefully that makes sense. Then I've got beta, which I'm just going to round from above. Excellent. So we can enter that. Now I'm going to define a data frame called portfolio. So pd.dataframe. And I'm just going to use all this information that I've got there. So stock, what's the stock going to be? Well, that's going to be the stock list that we defined right at the very top. Better put a comma there. We're going to define the direction. So what do I mean by direction? I mean long or short. Are we buying or selling these products? And for all these shares, we're buying, so we're going long. What's the type of these products? Well, everything I've got here is a stock. I'm going to call that S. I want to define the stock price, and that's actually going to be different to the product price. So we're going to call that the stock price as price, and we're going to have the actual asset price, which could be different, as the price of the instrument. Now, why am I separating those two? Because I'm going to add options into this portfolio. So you'll see that there's a difference between obviously the underlying price and the price of the instrument you're buying. So units are going to be equal to units. Value is going to be equal to value. The weights are going to be equal to the weight, and beta is going to be equal to beta, you guessed it. And the weighted beta of this portfolio, all I need to do is multiply the weight by the beta. Excellent. So if we print out that, we're going to get this lovely table here. So you can see that we've got the stocks, the direction, the type, the stock price, the price of the instrument. Remember, it's going to be different in a second. The units, so the number of stocks, the value of those units, weights, I've cooked that, haven't I? Weights, and the betas, and then the weighted beta. Now, you could sum those weighted betas and use that as a proxy to see your total portfolio value, how much that can vary over time. But what happens if we're going to add options into here? It suddenly gets a little bit more complicated. So it's actually better to think of these things in terms of delta. And what I mean by delta, I mean when we have a change of 1 in a specific unit, what is the change in value of that particular product? So let's just get into it, and I think you'll see what I'm talking about here when I start adding these options contracts into this portfolio. So to consider options, we're going to get rid of the weighted beta and the weights column. We no longer need that. So the way we can do that is we can go portfolio equals portfolio dot drop, and we're going to index the columns we don't want. So we don't want this weighted beta, and we definitely don't want the weights. Cool. And we're going to drop on axis equal to 1. What we do want is we want to define something called delta. Now, delta for just the stocks is going to be equal to the units. So you can think of it, if we have a price change of $1 in one of these stocks, obviously our portfolio change, well, that specific instrument change is going to be $1 per unit. So I'm just multiplying $1 by the number of units. Hopefully that makes sense. So I'll print out that data frame now. So now we've just got beta and delta. So if the stock price here, or CB, changed by $1, that individual position is going to go up by $100 because I have 100 units. So obviously very simple calculation for the stocks. What about for the options? So here, I've got 3 options here, and I've just got details. Essentially, you've just got to go to your brokerage website or whatever, the stock exchange that you're looking at, find out all these pieces of information. So I've got these specific options. I've got CBA and WPL. I've got the prices, the number of units that I'll be buying or selling, the deltas associated with them, the direction that I want to be. So short this call type on CBA and long this put. I haven't added the strikes in here. They're irrelevant for this calculation, but obviously it matters a lot to you, and it determines what the delta is. So yeah, you can just add different options and go find these bits of information for yourself. So I've got a list here of dictionaries, a dictionary for each option, and I'm not bothering to type it out here because I didn't want to bore you guys. So the way I'm going to add this to the data frame is iteratively. So let's just go ahead and we're going to go for index and row in enumerate options. So for each one of these options, I've got a dictionary. So I'm going to take the portfolio and I'm going to add a row of this specific instrument. So I want to index the row option and make that my row title. So that'll be that symbol right there. So what I want to add is all of these column values. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 column values to add. So we need to calculate it from this information here. So the first one is underlying. So what is the stock name? That's easy. So comma. The next one is the direction. So row direction. The next one is the type. So you can see here that it's just a bit of a tedious process actually calculating these all and getting them into the data frame, but it's so it looks nice, and so you can see what I'm talking about here. So the type, we've got the next part is probably one of the harder ones, so we need to get the stock price for this underlying. So we're going to take the portfolio information, we're going to take this, this table right here, and we're going to use the lock formula. So we're going to go, what is my underlying? And that should return the symbol right here. But you can see that it's without the AX, so I've got to go string plus string dot AX. What I want to return, I want to return the price. So you can see here that we've just got portfolio lock on the underlying and the price. Excellent. So the next piece of information we want is the row units. I've defined them. Next piece of information we'll want is the row price. Now, here's an interesting one. So we've just got the stock price, now we want the price, which is going to be the option price there. That's fine. Oh, sorry, I've done that the other way around, sorry. So it's price before units. Cool. Units, value is just going to be the price times the units, but for options, you need to be careful about the option multiplier. So we've got 100 different underlying per unit. So 100 units of shares for one option. So I've got 2 options that I'm buying or selling, 100 shares on each of them multiplied by the option price. So make sure you understand the option multiplier. Now the beta, I need to refer to what the underlying is. So again, we're going to take this row underlying information plus the AX. Then for the last one, probably the most complicated, is the delta. Now, how are we going to calculate the delta? It's going to be plus or minus depending on if we're short or long. So it's going to be row delta multiplied by row units multiplied by 100 shares. Now it's going to be positive if row direction is equal to long. Else, we're going to take the exact same thing, but put a negative in front of it. Awesome. Okay, so that was a bit of a painstaking process, but obviously if you spell something wrong, this index wasn't correct here, so it was capital P for price, no S on the end. So just fix that up. Copy and paste it from my website if you get lost. I obviously need to do the exact same thing. So now we get this data frame here. And you can see that now we've got the correct calculated delta for our short position on the call and our long position on this put. So that's pretty cool. What we're going to do is we're going to weight these deltas and then summate them over the portfolio to get an indication of, given a change on a particular, on the index, what is the change of value of my portfolio. So let's weight these deltas. So the way we're going to do that is we're going to define another column, and we're going to define two columns. We're going to define ASX 200 weighted delta. So this is going to be a per point. So remember the index is per point, but another handy thing, because it's so large, will be, you know, what if we have a 1% change of this index? So that might be more useful in terms of looking at it and see if I have a 1% increase in the value of the portfolio index, what is my likely increase in my portfolio? So we're going to round this, both of these things, to 2 decimal places. So what I need to do is I'm going to take the portfolio beta column, and we're going to multiply that beta column by the stock price. So we got the stock price. We need to normalize that by the ASX price. And remember, we're going to index that by 0 to get the ASX index price. So we're taking the stock price, dividing by the benchmark price, and multiplying that by the beta. Hopefully that makes sense. We're going to take that number and we're going to multiply that weighting by the portfolio delta. So we're going to do the exact same thing for this 1% case here, except instead of getting it in terms of a per point, we just need to multiply by 0.01 for a 1% change. Let's return our portfolio. So as you can see here, we've now got the portfolio weighted delta in terms of a single point change on the ASX, but currently the ASX 200 index is up at like 7,000. So, you know, if per point, usually it's changing maybe 2%, 3% per day. And that's a number of these points. So it's kind of not useful to us. But if we look in terms of what happens if I have a 1% change in the ASX index, then you get a much more easy value to understand. $100 change for my CBA position. A negative $126 change in my option position, my short call position, with only 2 units. So that's really interesting. So you can see how we can use these options to our advantage to try and balance the actual impact of a market move. So let's final step is sum up on that last column. So we can see the total portfolio altogether. So let's call this row total, and what we're going to calculate the sum of, we're going to calculate the sum of the value column. I'm just going to copy and paste these because I don't want to make a mistake. So we want to sum up all of these columns. Yep. Hopefully that makes sense. And we're going to make that equal to portfolio value ASX. Let me put that on the next line. Backslash equals portfolio value ASX weighted delta point and ASX weighted delta 1%. And I just have to go sum. So all we're doing is creating a final row where we can then see the totals of these positions. So as you can see there, we've got the weighted sum of this position. If we have a 1% change in the ASX index, we have about a $240 impact on our total portfolio. And you can see here that these short position on the call, long position on the put, these have actually aided into reducing our direction in terms of market movements. So pretty cool from a risk perspective what you can do with these options. Really handy to understand beta and how you can then use the betas of these portfolios to be able to get some kind of judgment on percentage moves in terms of a reference. And again, this reference I've used for the ASX 200 index. You could use whatever reference or benchmark you want to. I guess a really handy thing for this is that if we were doing it in terms of ASX 200, it would be very easy for me to directly calculate how many index options I would need to hedge this portfolio to a certain amount, I guess. So yeah, so just in summary, something that's really important to remember is the time frame you're calculating these betas over. So remember, I just did it from the start of 2021. So up here, when you first select your date range, be really careful what data you're specifying because that's going to affect the correlation and therefore impact your direction of all these positions. So as always, thank you very much for listening to ASX Portfolio. If you enjoyed the video, go ahead and like and subscribe for more content like it. See you later.